Okay, so welcome everybody back to our course, Programming 2. And yeah, I'm very happy that we have another, well, it's not really a guest lecture, I would say, because the lecture on Smalltalk is given by Professor Oscar Nierstrasz, and maybe some of you or all of you know, so he was my predecessor here at the University of Bern for many, many years. And actually, Oscar was already contributing to the development of object-oriented languages and to research on object-oriented languages and software engineering when I was not even in elementary school. And so he is talking today about Smalltalk. I mentioned Smalltalk from time to time as an object-oriented language that is way older than Java and goes back almost to the origin and to the birth of object orientation. And some things we talked about, so you remember these three views that we talked about that you can have when you look at object-oriented programming. The one we took mostly, I think, is the software engineering view. Maybe a bit biased because of my own research on software engineering, but you may well remember that there are other views on object orientation, especially the mystic one, like objects sending messages and communicating with each other. And this is, well, you can think about this when you program in Java, right? Your mental model is like objects sending messages, but it's not that clearly visible. And there are some nice things in the Smalltalk programming language, and Oscar will tell you about the secrets. I think this is a very special lecture that is not given very often at universities because, well, most of the people simply do not know the Smalltalk programming language very well, including myself. So I'm very happy that Oscar offered to give this lecture. And, well, now I'm quiet because I think you have much more interesting things to tell. And the stage is yours.
Thanks very much, Timo. Thanks very much. Thanks very much for the introduction, Timo. I'm very happy to be here as a guest lecturer after teaching this course for something like 27 years. So it's nice to be here in a much smaller role. Yeah, I would like to tell you a little bit about Smalltalk today. It's a programming language which people don't talk about, a little bit like Fight Club, I think. It seems to be a bit of a dirty secret. So when there are systems implemented in Smalltalk, people don't talk about it because most of the developers out there are focusing on other languages and technologies. But I hope I can convince you today it's a very powerful, very interesting technology. Even though it's one of the oldest object-oriented languages, it still has a lot to offer. What I'm going to be showing you, this slideshow, if I can call it that, has been prepared with technology that's developed in a company that I'm working now called Think. And they've been developing this really amazing software development and analysis platform called Glamorous Toolkit. So this is all implemented in GT. I'd like this to be a little bit interactive. As you'll see, the slideshow itself is going to be interactive. So if you have questions, the environment you'll see, a lot of things will look familiar, but a lot of things will look very strange. And I don't want you to get lost, so please ask questions. It makes it more fun. Then I can jump out of the fixed narrative and we can talk about other things too. Just to give you a little bit of an overview, as an appetizer, what I thought would be interesting, collaborated with Pooja, we went and implemented your exercise in Smalltalk. So this is the Ludo game, or Mensch ärgere dich nicht. And as I said, this is a live thing. So here, for example, player A has to roll the die. This is an actual implementation of the game here. So you can just play through it. Of course, nobody gets a 6 here. It'll be a while before we get one. But we'll be returning to this example as we go through the lecture today. So this was going to be a running example. But before we do that, I think I want to tell you a little bit about some background. So this is a rough outline. First, I want to tell you a little bit about Smalltalk, what its origins were, Because the syntax and the appearance of the language is a little bit different from what you've seen before, I'll spend a couple of slides talking about syntax. Syntax is usually kind of boring stuff, but there are some weird things, so it's good if you've seen them, and that'll help you to see, understand what comes later. One of the key things about Smalltalk is it's a live programming environment, and I hope that'll become clear what I mean by that through the demo and presentation today. So one of the key things is that we can have live interactive views of objects, and we'll be seeing lots of those. I also want to show you a different approach to testing. You're doing lots of unit testing in the course, and of course we have unit tests in Smalltalk, but GT has a particularly interesting approach to testing, where each test also delivers an example that you can use to build new tests or to explore and continue to work with. So in tests, instead of just running, we'll also deliver you an object that you can interact with. We'll also see how you can prepare live documentation with notebooks inside GT. And notebooks might make you think a little bit of Jupyter notebooks. These are called Lepeter notebooks. But they're also live programming notebooks as well. So in fact, a lot of the slides that we'll see are just going to be notebooks that allow us to wander through a number of different examples. And then I'll try and wrap up with some of the most important take-home examples. So Smalltalk originated some 50 years ago, believe it or not. So it was in the 1970s that Alan Kay, actually late 60s, he became convinced that we needed new kinds of programming and development environments, because he saw that computers were becoming faster and cheaper and smaller. But you see at the top left there is something that he called a Dynabook. And he imagined in the late 60s that some 30, 40 years later, people would be able to hold a computer in their hands, and it would be a multimedia device filled with books and encyclopedias and all sorts of things that you could interact with. That's just a piece of cardboard there, so it's not a real prototype from the 60s. But he said if we're really going to build these things, we have to be ready for it. And we can't build them with the languages and technologies that we have at this time. He was very inspired. He met Ole Johan Dahl and Christian Nygaard in Norway. They had developed this language called Simula, which was an extension of a traditional language with the concepts of objects and inheritance. And it was more conventional compiled language, just with some add-ons of objects and inheritance. But Kay said, you know, if we're really going to build these kinds of new environments in the future, we need not just a language, but an environment which is fully object-oriented all the way down to the bits. Like everything, absolutely everything should be an object. Not like in Simula, where only the things that you simulate in real-world simulations are objects, and the rest are just algorithms and data. So he said, what we want is a real, purely object-oriented language and system. They prototype all sorts of crazy ideas. They've even built the hardware. So that's an Alto. That was one of the first graphics workstations built in the 1970s at the Palo Alto Research Center. And they built the first windowing systems and the first interactive development environments. Looks kind of clunky today, but this was amazing back then, nearly 50 years ago. Glamorous Toolkit is an environment that's built up on top of Smalltalk 80. So Smalltalk 80 was produced by Kay at the end of the 80s. And there were all sorts of implementations that were built on top of that reference implementation. And in fact, GT is built on one of these genealogical spawns built on top of a modern open source software called Faro. And what GT adds is a complete new windowing and windowing framework. So it looks completely different from your standard Smalltalk environment. One of the key emphasis is on moldable development, and this means that the environment itself can be molded or adapted to your applications. And we'll see that a little bit with the Ludo game. So you have native windows, all sorts of tools for software and data analysis and visualization. And yeah, we have slideshows here. By the way, this is the Glamorous Toolkit environment here, running inside the slide here. Here we have notebooks. We have playgrounds where we can execute stuff like 3+4, and everything's an object, as we'll see in a moment. So this is the actual environment here. So you have playgrounds for running stuff. You got notes for taking notes and notebooks, which are a variant of the playgrounds. We have a full coding environment, which looks rather different from the usual IDEs that you'll see. We'll play with them a little bit. And all sorts of other tools. For example, there's access to Git repositories, code changes, and so on and so on. I mentioned a couple of times that Smalltalk's a live programming environment. Now, what does that mean? So unlike most of the programming languages that I'm sure you've used, I'd be surprised if any of you have been working with a live environment. So in a live environment, so in a classical programming language, you write some code in a text editor or some glorified text editor, then you pass it to a compiler which compiles the code, and then you execute it, and then you can see your program run. In a live environment, you're always inside the running program. So here, I'm right now inside a Smalltalk environment where all the objects are available. And if I want to program, I don't go outside of Smalltalk and edit in my favorite editor and compile some stuff. Inside the Smalltalk environment, I program a few lines of code. I program a new method. I introduce a new class. And that change is immediately made. And it adapts the actual running system. There are 4 important pieces. So you have something called the image. This is where all the objects live. You have a virtual machine, which is like a Java virtual machine. Then there's also all of the changes that you make. And these are, the moment you make a change, it's filed out to disk. So it's actually saved somewhere safely. And you also have the sources of that version of the system. So those are the 4 most important pieces. Why is code changed? Code changes logged? Well, because Smalltalk lets you do anything. In particular, it's very easy to shoot yourself in the foot because, I mean, you either have an environment that doesn't let you do certain things, and that's very frustrating, or you have a system that allows you to do anything, including shooting yourself in the foot. So you don't shoot yourself in the foot too often, but when you do, you can start up a fresh image and go back and load back all your code changes, and you normally shouldn't have lost anything. And that's a real lifesaver. It's important if you're doing anything that is making changes to the core system itself. And normally when you're programming, that's not the case. So it's very rare that the system will crash on you. But if you're working on an unstable version of the system, or if you're actually developing the system itself, it's important to have this fallback. OK, now a little bit about Smalltalk itself. I want to watch the time. I don't want to spend too much time on the basics. Let me get into the fun stuff. But I think this is important. So you've been all programming with Java, and I imagine lots of you have used other object-oriented languages. So aside from Java, who's been programming in what other languages? Who's been programming in Python? Lots of people. Other languages, C++, C#, PHP. Other languages that I didn't mention, yeah? C, object-oriented languages, other O languages? We've covered them all? Okay, so all of the languages that we've mentioned, some of them are statically typed and some of them are dynamically typed. So some you have to explicitly declare the types of things, some you don't. But these are all mostly static languages. You write your code, you compile it, and then you have your running system. None of those are live programming systems. Now, how do things work in Smalltalk? Smalltalk goes a step further in that everything is supposed to be an object. So this is the one thing that you have to remember. And the second thing, yep?
Just one question. A language is interpreted instead of make it directly.
No, absolutely not. In fact, I think the distinction between compiled and interpreted is completely bogus today, because all the languages that you think of, I defy you to name an interpreted language. I don't think there are any, because they're all compiled to some kind of bytecode, and that bytecode is then highly optimized to a virtual machine and maybe just in time compiled to machine code. So what on earth is an interpreted language? I don't know any. I would never call Smalltalk an interpreted language. It's a compiled language. You compile to bytecode. And just because it's bytecode instead of machine code doesn't mean it's interpreted. But yeah, to have a live environment means that you're in an environment where you change the environment while it is running. And you don't want that in Java. Java explicitly disallows that for all sorts of security reasons. So you can say, okay, so if we're programming our system in Smalltalk and people know that the system can be changed on the fly, maybe our customers are going to be very nervous about that. And okay, so that may be one of the reasons that people don't like to know about it. But Smalltalk really is a very nice environment for many kinds of applications, particularly for data and software analysis. Okay, everything's an object. And second of all, everything happens by sending messages. This is sending messages stuff. So this is exactly the mystical part of object-oriented programming. Think of the word method. Where does method come from? And you execute a method or you run a method. What does that mean? It makes no sense in English. I have methods for doing things, but I don't run a method. It makes no sense. I'll get back to that in a second. First of all, let's have a look at everything as an object. Maybe this is a bit small. See if I can zoom in a little bit. So everything is an object, and every object is an instance of a class. So that means absolutely everything. So go right down to the bits. So here we have the number 1, and here, so actually the thing that's on the left there, that's a notebook filled with text snippets and code snippets. And I prepared those in advance, but I also embedded that in the slideshow so that I could reuse it. But you can also have a look at it outside. And here we're inspecting this object. So this is an inspector view. And it's got all sorts of different views. We have the preview view of it, so we see it's a 1. An integer view of it that shows us what this integer is in all sorts of different representations. There's a raw view, which shows us what are the instance variables. As you can imagine, the number 1 isn't terribly interesting, and so on. There's a print view, and there's also a meta view. The meta view is the code view. So it shows us the actual implementation of the integer in Smalltalk. Integers, the implementation of, what's going on here? So in Java, you won't find the implementation of integers. You'll find the integer class, and you'll also find an int. But the integers are really implemented in the virtual machine. Well, it's a bit of a cheat in Smalltalk. Of course, at some point, you hit the virtual machine. But you have the illusion down to the smallest fine-grained objects that everything really is an object, and that works. I can add new methods to the integer class and make it do new interesting things. Hello is a string, so it's an instance of a byte string here. We can have a look at that. True is a Boolean value. It's an instance of a class. It's the class true, and its superclass is Boolean. And this thing is a block, so in square brackets. So it's a block that can be evaluated. So here's the source code, and I can actually evaluate this guy. I can say, hey, what's your value? And I can say, hey, I'm sending the message to self, that's Smalltalk for this, and I send it the message value, compute to your value. And there I get it. I get the small integer 7. So I can interact with these things. I can not only evaluate things, I get the objects right there in hand, and I can talk to them. I can explore them. I can have all sorts of different views. And as we'll see, these views are extensible. That's where the environment is actually moldable. So I can add new views if they're useful to me. Okay, this is perhaps not so surprising so far. Let's get rid of these. Everything's an object. So objects are instances of classes. Well, classes are things, so they're objects too. So for example, small integer, I can browse the class small integer, but I can also inspect it. I'm using keyboard shortcuts here, B for browse and G for go to this object and explore it. So this is the class view. So this is a small integer class. And here's the raw view. I can see that the class as an object is really in the system. It's there. And I can see it has fields for the superclass. It has a dictionary of methods. So here are all the methods of the small integer class. And I can walk through them and I can explore them. I have other views. For example, for classes, it's interesting to know what the subclasses are. So there's a view of that too. Classes are objects, so I can send messages to them. For example, oh, I forgot to say. So in Java, classes are not objects. Classes can be reified. I can ask an object, hey, give me your class. And that means Java will create an object that represents information about the class. But it's not really the class. Here, if I change this class now, I will change the implementation of all small integers in the system. That's one way I can shoot myself in the foot. In Java, I could try and change that object, but it would have zero impact on the system. So it's not really the class of the object. It's just a piece of data that represents information about the implementation. I can send messages to these objects. So for example, there's a method maxval that tells me what's the biggest integer in the system, which, as you can guess, is going to be how big? Anybody, come on. First-year computer science students should be, what is that number? Yeah, that should tell you. Should be 2 to the power 32 minus 1 or something like that, exactly. So what would happen if I add 1 to it? What do you expect in a reasonable programming language to happen? It's the biggest possible small integer that it can have. If I add 1 to it, the system should crash, right? Well, of course not. Then I get a large positive integer. And if I subtract 1 from that, it's amazing. All of these snippets are still cached here. It was a long time ago. Then I get a small integer again. So I don't have to do all this jumping through hoops to explicitly create a big integer and so on. It just happens automatically. So I get big numbers if I really want them. So for example, if I do 100 factorial, that's going to be a big number. Yeah, it's a big number. So, I mean, it's not a problem. You can deal with very large numbers. Everything's an object. We talked about methods. Methods are objects too. So for example, I can send the message even to the number 4, and it tells me that's true. Even is, here's the source code. So it does a bit and with 1 and checks that that's equal to 0. So that's a nice implementation. I didn't know that. Okay, but this is actually an object. So if I can click on it here, oh, where did it go? Well, I can send the message greater than, and then there's this hash even, that's a symbol, and I say to the class small integer, hey, look up this message and give me the method corresponding to that, and I get here a compiled method. There's its source code. I can look at its bytecode here. So this is the bytecode that's executed for the compiled method that we just saw a moment ago. And I'm not great at reading bytecode, but you can sort of figure out what's going here. So yeah, we push the constant 1, and then we send the message bit and to that, and then we compare it with 0 and return the result. So that's how even is computed. But this is an actual object, compiled method there, and it's sitting there in the system. It's accessible to me. So that's an object. Everything's an object. This page is an object, the page that I'm looking at here. So if I ask this snippet, so this snippet is a little extension to GT. This snippet is that little snippet that says this snippet page. That's a little bit of code there. So I ask this snippet, I send a message to it, tell me what's your page. And I send that message, and I get the page back. So now I'm inspecting this page in an inspector here. And I can look at, for example, I can see that it's an implementation of the class, an instance of the class Lepiter page. I can look at its raw view, which is not so interesting. It tells me all the bits and pieces. But there's some dedicated views. So here are all the snippets and nested snippets inside this page. You get the idea. The Ludo game is an object. So I can send the message new to GT Ludo game, and there I get it. Now I'm inspecting that instance of the Ludo game. I have a bunch of different views. I can see the state of the board initially. I can see who the players are. I can see which squares are on the board. They're all numbered. There's nothing on the squares, so it's not very interesting. I can also see the raw view of the implementation. I can jump to the meta view and see its implementation that we created in GT. Tools are objects as well. So I can get a coder for the class small integer. So this nice interface that we saw is actually just an instance of an object, and we have different views of it as well, including its live view, and we can also look at its meta view, so the implementation of the coder view. Even this slideshow is an object. So here it is. It's got a bunch of slides, and there's the live view, and I'm on, I don't know which, let's look at one of these. So this is the first page and the second page, and somewhere here is the page that we're looking at now. Right. So those are all objects, and you can just walk through them. And the world is an object, so we saw that one already. But we can also inspect it and explore it. So the key thing is everything is there all the time. And if you want to understand what's going on in the system, you say, how is that implemented? Well, you can just try and get a hold of an instance of that object and navigate, and you can explore it, you can send messages to it, you can investigate its implementation, and so on. So this is all really, really live. So 1, everything's an object. 2, everything happens by sending messages, really everything. Now, where does the sending messages come from? The term method was introduced in the group of Alan Kay, and the whole mystical view of objects says everything happens because I send a message to an object. I don't manipulate data. So if I want Timo, if he can help me with something, I send a message to him, hey, Timo, can you do this? I don't open him up and look at his implementation and poke about inside. He wouldn't really like that very much. But I just ask him politely, hey, can you do that for me? And Timo says, yeah, I know how to do that. And he has a method for doing it. So I send the message, and he has the method. Message and method are two different things. Message is what I ask. The method is how Timo does it. If Timo doesn't know how to do it, he says, I don't know, maybe I'll delegate that. I'll ask Pooja. So he sends a message to Pooja. I don't know that. As far as I know, Timo's doing everything. Poor Pooja's in the background, and nobody knows the hard work she's doing. And it seems as if Timo has done this for me, but I get the result back, and I'm happy. So this is the mystical view of objects. Sorry, Pooja. So a message is a request for a service. So everything happens by sending messages, even 3 plus 4. 3 plus 4 is sending the message plus to the object 3 with payload argument 4. Here's the message is plus 4. Here's the method. The method is the implementation that the number 3 knows how to do that. In this case, it's the primitive, so it's actually going to be done by the virtual machine, but we don't care about that. So at some point, there's a method, and if it's done inside the Smalltalk system or eventually at some point you hit the virtual machine, something actually has to happen. Every computation is a message send, so there's no built-in operators at all. Everything is happening either by sending messages or eventually by primitives. 3 divided by 4, that's not syntax, that's just a message. And this is sending the message divide by 4 to the number 3, and it's going to give me an instance of a fraction back. So what is this? This is just a factory method. It's a factory method that is eventually going to, well, we'd have to run through it. Eventually, it's going to ask the fraction class, hey, create an instance with numerator 3 and denominator 4. Other examples, yeah. Oh, there's like in all object-oriented languages, the distinction between equality and identity. So in Smalltalk, equals is a method that asks if 2 objects are equal as values. Equals equals says, is this the same object? The same identity, literally the same object. So those are different things. And you'll find that every object-oriented language makes a distinction between these two concepts. And they're usually syntactic variants like equals and equals equals, and I think in some languages even a triple equals. Yeah, you can send messages like value to a block. Objects are created by sending messages to classes. So here, if I want a new list, ordered collection in Smalltalk, I just send the message new to the class. And now I get an empty ordered collection. Or if I want a fraction, instead of using the factory method, I could explicitly send the message numerator denominator to fraction. I'll show you some of the syntax of messages in a moment. Notice there are different ways of sending messages. We have the operators, we have these single messages like value and new, and this is something interesting, this keyword style messages, which might remind you a little bit of Python has something similar to that. So whereas Java, I would have a message fraction dot create numerator denominator inside parentheses. Instead, in Smalltalk, I send a keyword message. So a message with a whole bunch of keywords and the arguments all separated. What's nice about that is it makes it a little bit more readable. So you can, if you design your interface nicely, you can read it out loud almost like English. So fraction, numerator 3, denominator 4. That rolls off the tongue much more easily than fraction dot create 3 comma 4. It just sounds a bit better. Oh, a set with 3 and with 4, that gives me a set object. I can also change the system. Now, usually when I change the system, I'm using the IDE, a coder. But I can also, everything happens ultimately by sending messages. So I could actually create new code by executing a bit of code. So here, for example, if I want to create a new subclass of the class object, I will take the symbol, hash my class, and I say, hey, object, please create a subclass. So now I have a new class in the system. I just changed the system on the fly. So there it is, my class. And I could create an instance of this. So now I have an instance of my class. It's not very interesting. It has no methods. It just inherits from object. But I could compile a new method called foo that returns 42. So if I evaluate that, here I get, here it's been done. And now let's create a new instance of, oops, excuse me. Now let's create a new instance of my class. And now it has a foo method. So if I actually send self foo, so this is the instance of my class that I'm sending this to, then I'll get the 42 back. So now I've made 2 changes to the system. I've created a new class, and I've compiled a new method. And I can also get rid of this. So if I do this, this class is now completely gone, and it's not in the system anymore. Obviously, normally you wouldn't program that way, but it's useful to understand that everything that happens in a tool is actually happening programmatically at some level. Okay. And you can change anything. So I could, for example, try to remove the class named object. In this particular case, the system won't let me do that, but I could do other nasty things that would break the system in irreparable ways, and the whole system would come crashing to a halt. So normally you shouldn't do that. Smalltalk assumes that you know what you're doing, and if you don't, there's a fallback that you can recover from catastrophic changes. Okay, that was a quick introduction. I have a couple of slides that I can go through very quickly, just to show you a little bit more of the syntax. I won't spend too much time on them, but if anybody has a question immediately, maybe now's a good time to ask. Not store them up. Yeah?
Yeah, so you do a debugging run.
Yeah, so here, for example, I just installed a breakpoint in the method factorial, which is part of the system. So I just send the message halt to myself. So that will, if I save that, oh, why doesn't it want me to save it? Hello. Factorial guy. Can I not do that? Self-halt. Something is strange is going on. Ah, that's why. Yes, it's invalid. I put it in the wrong place. So it shouldn't be before the original declaration. So if I put that here now that'll work. So now if I evaluate this, I can run it, or I can even just directly debug it. And I hope I didn't crash the system. Oh, that should work. no recursion there. There's no reason that should have. Oh, maybe it's the debugging feature. Let me just quickly get out of there. I'm not sure why it didn't like that. It may have been something. Okay, in any case, let's try that once more. Self halt. Hello. Oh, wait. I think I shouldn't be doing that here. Real demo effect, sorry. No, but let me just do it in a playground. So for factorial, and we go to the factorial implementation, and we can put a self halt here. I don't know if I'm having problems with the, could be exactly that. So now if I evaluate that, then a debugger will pop up. And here I'm in the debugger, and I can explore the whole stack. I can explore objects. Well, this is not a terribly interesting one. I can make changes to the system. And in particular, I could, even while I'm in the debugger, I can get rid of this change and continue executing and get the value. So while you're in the debugger, you can do any changes you like and continue executing, including hot compiling new code. So that usually works. Of course, it can get confused, but basically what happens, if you want to know more technically, the debugging stack is not really in the image. Where is it? Where is the execution really happening? Where is code running? Where is the runtime stack? Exactly. The virtual machine is not in the image. The virtual machine is in, the runtime stack is in the virtual machine. It's not in the image. So what happened there? I had the debugger and up popped, and all of these objects, the runtime stack was suddenly in the image. So that's part of the magic. So when you get this debugging thing happening, the virtual machine at that point reifies. To reify means to turn into objects the entire runtime stack, puts it in the image, and starts up the debugging tool. And now you're in a different environment where you can actually step through execution inside the image. So you have the illusion always of being in one and the same environment, but there's sometimes some real interesting magic going on. So that works, but technically there's a lot of interesting magic going on in the background. Yeah.
I was more asking the other way around. So when I do in a restart and recompile.
I think more modern debuggers learn from Smalltalk, and they try to make the debugging environment. Yeah. So what I'll do is, we're close to the break. I'm just going to plow ahead and go very quickly through a couple of slides of sort of the basic stuff so that then we can, after the break, go more deeply into some of the more interesting things. So I think the background is important. So we have three kinds of messages: unary messages like 5 factorial, float pi, sending the message pi to the float class, sending the message new to a class to create an instance of it. And then we have binary messages like 3 plus 4. There are a whole bunch of binary operators, and you can overload them. So you can't do that in Java, but you can in C++ and lots of other languages. So you could define plus for your class, or here comma is, by default, it's used for any kind of sequence collection, including strings. So they'll concatenate things together. And less than, here this is actually going to be a left shift. So take the number 1, left shift 10 bits, and I get 1024. Then we have the keyword messages. So they have multiple keywords with their arguments, like 3 raised to 10 modulo 5. And I have a keyword message for the Ludo game. So I can instantiate the Ludo game and send it the message, hey, roll a 5 on the die. And there I get an instance of the Ludo game, which has 5 rolled. The precedence is first unary, then binary, then keyword. So here, if I say 2 raised to 1 plus 3 factorial, that's the same as 2 raised to 1 plus 3 factorial, like so. As a consequence, computation is always left to right. There's no precedence over the operators. So 1 plus 2 times 3 is 9. That's not usually a problem. If you don't like it, then add parentheses, and then you get 7 instead. So it looks, oh, that's horrible. Smalltalk's a terrible language. I've never had that be a problem for me. So you have languages like, I think, for operators in C++, I think there are 10 different levels of precedence. Smalltalk has 1, and I wouldn't say that I would prefer, like I can't remember the 10 levels of precedence in C++. Another one, just very quickly, there are some funny bits in the syntax. So you have radix numbers here. So in the binary number, so 2R says this is binary. So that's 101010, that's 42. And you can also have hexadecimal, that's also 42. Characters start with a $sign, that's weird. So that's the character A. And strings are in single quotes. So this is the string hello world. So the first character of hello world is $H. And double quotes are for comments. Okay, it's not slash slash or slash star or whatever. So this is not an object. So that's nothing there. There's nothing there. Nothing to see. So don't follow. That's a mistake that everybody makes. They type and say, oh, nothing's happening here. Yeah, because that's a comment, not a string. A comment is not an object, but the class may have a comment. So if I send the message comment to the Ludo game, then I'll get its class comment back, and that's a string. But that's something else. We saw some symbols. A symbol is like a string, except it's globally unique. There's only one of those. And they behave just like strings, so they are not identical. So those are 2 different objects. But from the equals perspective, equality, they're considered to have the same value. So if it's a string or if it's a symbol, the value is considered to be the same. So here we see the difference between equals and equals equals. There are only 6 keywords in the whole language. Here are 3 of them. 2 more are super and self. So nil is a constant. That's a nil object. True and false are constants. Self and super are keywords. And there's another one called this context, which I can tell you about in the break if you want, but you don't need to know about it. It's kind of like this snippet, and it has to do with the runtime environment. Arrays are also literals. So this is a nested array. Usually you don't use arrays, but ordered collections. But if you want to have a compile time thing, here's an array of 4 parts, and the 4th part is also an array itself. Then we have blocks. Blocks can also take arguments. They can take multiple arguments. And they're first-class values. So here I have a block that takes as an argument another block, and it will evaluate that block with another argument. So all the functional things that you know from functional languages you can do here as well. So just so that you've seen this before. The square bracket notation is a little bit weird. So these are all the things in Smalltalk that might surprise you if you've not seen them in other languages. And those are the pseudo variables, self and super. And there's a puzzle for you that you can cogitate over during the break. What's the difference between self and super? Because what's the answer to this question? Does self equal super? Think about it quickly, because I'm going to give you the answer. It's true. Self and super are the same object. Okay, you can think about that over the break. And then after the break, oh yes, I'll show you a little bit about method syntax, and then we're going to dive into a live exploration of the Ludo game. Okay, let's take 10 minutes? 10 minutes.
10 minutes?
15 minutes? 10 minutes? 15? Okay, 10, compromise, quarter past.
Okay, of course, quarter past.
Okay, let's take a big break. I need a break.
But the first conclusion starts with the fact that self is the same object. Because you're not used to think about self and super as objects.
In Java, actually, super is a method.
Super is used in multiple contexts in Java.
It's just a keyword that, depending on the context, means something.
Yeah.
Discriminator in some cases to make clear what you want.
But it's not a separate object, like
So did anybody think about why self and super are the same object? So self, or this in Java, is always looked up dynamically. So if I send a message to self or invoke a method using this, what happens is that the virtual machine is going to look at, it looks within the method where that's being, where that exists. And if I send a message to this or self, what I do is I start looking in the class of that object to see whether that class has a method for that message. If it doesn't, it starts looking up the hierarchy all the way up to the root. And if it doesn't, it raises an error. Slightly different things happen in Java and Smalltalk. But basically, you start looking up the inheritance hierarchy. So what actually happens, which method you find, depends on the inheritance hierarchy, and it's dynamic. So when I write code that sends a message to self or this, I won't know until runtime what actually will happen. Because depending on what instance, what class that object is an instance of, different things will be found. Super is exactly the same, except it's completely static. What super says is ignore the instance, take a look at the method that I'm in, and look at the superclass of the method of the class in which this method is defined, and then start looking. And that's static, because the method, we know exactly which class that belongs to. We know what its superclass is, and we can determine without running anything which super method is going to be called. So it can be statically elaborated. So super is just a keyword that the compiler understands, and it'll do different things. They say, okay, if you're calling self, at runtime we'll have to look this up. If you're calling super, statically we plug this in. So we can see this example here. I just quickly wrote a little class. Oh, wait a moment, here's some code. print string is like toString in Java. So if I create any kind of object and say print string, then I will say I am an object in this case. So I'm an instance of object because I created an instance of the class object. And now I created a class A, and I overrode the method print string here to do I am super print string. So I take the inherited print string, which is the one from objects. See, I know it statically, so I can actually see which implementation that is. And I extend it. So now if I say A new print string, I say I am an A. Now I have another method, which is exactly the same thing, except instead of directly sending to super, I just cache it into a variable first. So I save super as the variable mySuper, and then say I am mySuper print string. Should be exactly the same, right? But self is super. Super only is magical when it's used as a keyword. And here I've assigned super, which is self, to a variable, and now it's no longer magical. In fact, you can see here the little gray triangle is gone because GT has no idea which print string this is going to be. So it's going to be dynamic. So this is the same as a self print string. So now I'm going to say I am self print string, which calls this one, and you get exactly I am an A. So self and super are the same object. It's only that super is magic when it's used in that context. Okay, enough of that. That's not really what I want to talk about. So let's go back to the methods. Just show you very quickly method syntax. So here is a method in the Ludo game, which if I have a token that is going to move somewhere, I want to figure out which place it's going to land. So there are actually 3 different cases. A token enters play on the first square of the route. So for every different player, you start at a different place. So I'm going to look that up. And second case, I move forward to another square. And the last case, I'm near the end, and I want to make sure that I didn't roll too many, because if I roll too many, I have to go back to where I was. So there are 3 different cases. I'm not going to dive into the code. I just want to tell you what this method is, because here I can see a whole bunch of different things in the method. So first of all, here, the method starts with the declaration of the message that's being sent. So this is the message, compute target for a token. So that's this thing here. Then I have a bunch of different kind of messages. There are unary messages here, like in start state, enter play first, and so on. There are binary messages like comma and plus. And there are keyword messages like route at target index, self die top face equals 6 and, so logical and. There are some temporary variables. So in a method, if I have temporaries, they appear in these OR bars here. But I can also be, and those are the temporaries I'm using. There's an argument to the method. I'm using self here. What else? I have some strings, but I also have some comments. The comments are gray, so they're not objects. I have some blocks. Oh, and here's some additional syntax. The caret is a special return symbol in Smalltalk. So that says I'm returning something. So there's no return keyword. There's a special symbol, caret. And I can use that anywhere inside a method, even embedded inside a block. And that'll do an early return from that method. And I don't have any cascades. Oh, an assignment. So colon equal is assignment. So in a nutshell, that's pretty much all the syntax there is. It's a bit weird to see it the first time, but it's not like 100 pages of syntax like you see in some programming languages. You can learn this in 15 minutes. That's all there is to Smalltalk syntax. Yeah. So that's an important point. So instance variables. So here I've got, there are 3 kinds of variables here, right? I have the temporary variables. These are within the method. I have the arguments to the method, and I have instance variables. Instance variables are private. They're private not just to, with respect to other objects, but all instances of the same class. If you and I are instances of the same class, I cannot see your private instance variables. So that's different from Java. If I have 2 instances of the same class and I declare instance variables private, if you're instances of the same class, you still have access to each other's instance variables. So private is fairly, so if you want to give access, then you create accessors. And then there's no distinction between public, private, and so on. So by default, all methods are public, all instance variables are private. Okay. So let's start diving into something a little bit more interesting. Let's have a look at the Ludo game. Here's the Ludo game. We have a whole bunch of different tabs here. So this thing here, on the left, we've got a notebook. On the right, we've got an inspector. So an inspector is what you often see inside a debugger when you're inspecting an object. And the usual view most inspectors give you are just this one, the raw view. So it shows you all the instance variables and their values. So what GT allows you to do is you can extend these guys and you can implement new views. So you can actually option click on these and find out what the code is. The code of a view is usually pretty tiny. So it's just 4 lines of code. Of course, I built up a fair bit of infrastructure because I had to design the graphical user interface for the game. But once I had it, I could reuse it for all sorts of other things, which was nice. And the player's view is a view of all of the different players, which their tokens are, what state the token is in, the start state or the end state or whatever. And it's also just a few lines of code. So I extended the environment and the inspector, so I have a dedicated view that makes it easy to look. And the nice thing is, once you have these, you have a cascaded view. You can start walking through from one object, navigate to the next one. So you have these Miller columns moving from one inspector view of one object to another object, and you can navigate through the whole system in a very easy way that way. Right. Yes, I showed you that. In the meta view, you have not only the methods of the implementation, you also have a class comment, and you also have all sorts of references. So these references end up being examples that, of the game. So here, for example, is here's an example that creates an instance of an empty board. And there's another, let me see, where are we here? So if we go to, oh, actually, let me leave that for the moment and, oh, what happened? Yes, please do. Not the spinning wheel of death, that's not part of the exercise. I'm not sure why this is happening. Oh, maybe because I'm not usually using the M1, so it might be an artifact of that. I'm just going to get out of that. I don't know why. It's very strange. Usually working on a different machine than this one, so I'm not sure why it's giving me the spinning wheel of death now and then. Right. So there's a whole bunch of examples here. That are examples of the game. So we have an empty game here. And here's one where player A enters token A. So if we run this example, it'll create an instance of the game and will show us the history here up into show us the state of the game after player A has rolled a 6 and has entered the game. So we can actually see the steps here. So we start with an empty game, we roll a 6, and then we enter with player named A. So it's a fairly simple scenario. This guy is an object, which means that we can continue to execute. So here, for example, I can roll a 4, and then a player A should move. So I can either move execute things interactively, because this is a full GUI here, or I can send messages programmatically. So here I've connected that. I can also access different parts of the game. So if I want to access the actual die object, I can. Hello. Oh, no, this is very strange. This is the demo effect. I swear this wasn't happening before. I should get the non-M1. I do not understand. Oh, that's very disappointing. It's going to be a little bit frustrating if everything I'm demoing for you is going to show up the same. Yeah, I'm usually working on an older generation Mac desktop machine rather than this one, and I thought this should have been pretty stable, but I'm not sure why it's...
So I saw it running, actually.
I have also proof.
It's okay. One thing that's kind of cool to see is all of the interaction is working. You did some experiments with Model View Controller. So all of this interaction is working the same way. So whenever there are GUI events, there are particular announcements that are raised, and these are broadcast, and vice versa. So when something happens in the GUI, the model is informed, and when something happens in the model, the GUI is informed. So here, for example, if player A rolls a 4, the multiple views are all updated in sync, as you would expect. And also, the different views are also updated. So here, if player A, oh yes, so here we have this squares view. So here, if player A moves, then, hello. Oh, that's also very strange. Ah, okay, finally it did react a little bit. Mouse problem there. So all of those things are working the way you would expect them to. Now, since you didn't see much in terms of working with a live system, but let's have a look at that now. So one thing that you might want to be able to do in a game like this is it's very boring clicking through the game just to get something to happen. And you can do it programmatically as well. But you know, the game is not so complicated. In any particular point in time, there are only a certain number of things that can happen. So why don't we let them happen randomly? So let's create a live instance of a game here. And while we have this game here, we're going to, first of all, we can roll a 6. So let's do that. And then we can move the token named A. So it's moved. That's fine. We can do stuff like this. But what we'd like to do is automatically play the game. If you explore the implementation, you see that there are various methods that tell us what happened next. So for example, there's the Ludo game player to roll, which tells us which player's turn it is and which player has to move next. So a little bit of exploration will expose how the game is working. Notice that the tendency is for a lot of these methods to be quite short. So most of them are one-liners. And there are only a few which tend to be a little bit more complicated. Which one was? Yeah, compute target for was a bit more complicated, and it's being used in the move token method, which is also a little bit more complicated. So seeing these longer methods is relatively rare. They tend to be, they're a little bit more complicated algorithms like these two, because the logic of moving in the board is not so simple. And the other case is if you have complex test scenarios. Of course, another way of solving this is the way you did it in the Snakes and Ladders game, is distributing a lot of the logic to the actual squares themselves and make them more intelligent. So you either have a little bit more centralized logic, like we put most of the logic in two methods here, or you could distribute it and then have a lot more finer grain methods. And it's a trade-off. Usually you'll start with one, and as you develop the code, you'll discover that, maybe there's a better way of doing it, and then you rewrite the code and refactor. And then it's very important to have tests in place. And we'll see in a minute that we have lots and lots of tests for this game here. What did I want to do? Yeah, let's get this instance up here. So we have an instance of the game, and we actually made a move here. We can ask which player is to roll, and so that we can be in two states. Either there's a player that has to move, or there's a player who has to roll a die, or the game is over. So if the game is not over, there are only these two situations. So we can say, well, ask the game, should the current player roll? And if so, well, let's roll. So we just do that. And if that's not the case, if it's a player to move, then we'll pick one at random from the tokens that could be moved. So let's do that. And now we can just combine these two things, and I can just start bing, 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 and start executing the game just by running this snippet over and over again. Well, you get the idea. So why not make this a method called autoplay? And autoplay is just going to run a certain number of times. Now, we saw before, I could do this in the coder, but I'm going to cheat here and just add this method dynamically here by compiling the code on the fly. So here, we've done that. And now I create a new Ludo game, or actually, I don't even need to do that. So let's go here, and I can autoplay 1. I can autoplay 10. Or I can autoplay 1,000 times. And if I autoplay 1,000 times, then my image will freeze. Why is it doing that? Oh, come on. Really? There's no reason for you to do that. It's just being mean to me. Okay, I do not know. I'm going to ask my colleagues why that's happening. And I go back again. Very strange. Nightmare of anybody who's trying to do live demos, which is why you pre-record things, but that's no fun. Pre-recorded demos. All right, so what did we do? I'm just going to be optimistic here and compile this again. So let's have a look at that. And let's do that 1,000 times. Will it work? No. Very, very, very annoying. Okay, I want to move ahead because there's more. I think there's something funny with this with it running on the M1. Okay, let's move ahead quickly to the example methods, and afterwards, if I have time, we'll see that again. One of the key differences to unit testing that GT is introducing is the notion of example methods. So an example method is just like a test, except the object that you're testing, that you're running assertions on, is returned at the end. So it returns an object which is an example. This is useful for two things. One, you can run the test, and instead of just seeing red or green, you actually have the object, and you can explore it, and you can do anything you like with it. You can explore it, interact with it. So here's an empty game. So here, the empty game is created. There's some things we expect it to be true, that the game is not over, the winner is no one, the current player is still A, the player is supposed to roll, but it's not ready to move. And then that instance is returned. So we could actually play the game from this point on. This is an ordinary method, but it's also labeled here with a pragma. So these angle brackets, those are like annotations in Java. So they're not executed by the method itself when it runs, but it's kind of a meta annotation. So there are tools that find it and they know what to do with it. For example, there are tools here which will find all the examples in a package so that you can run them all. So for example, if I move back here to Ludo, here's the package. All the examples are here in the examples sub-package, but if I just go to the examples view, here are all the tests, and I can just run them. And if this freezes the system, okay, so they're all green. But each one of these is actually a test case. So I can just run it, and I get the object, and I can see something. This happens to be an example of a move. What I did here, so this empty game example is actually used in another example. So the cool thing is, once you have a test example, the resulting object can be used as input, the starting point for another test. Now, the orthodox view of unit testing says tests should all be independent. This is a lie, because if you look at real tests for complex systems, you'll see that there are lots of tests with boilerplate code that's duplicating the same stuff over and over again. And I would say that the worst smell of the two, tests that are dependent on each other and having duplicated code, the duplicated code is the worst. So the cool thing is that as a consequence, you can cascade all of these tests together and use them for another one. So here I've got the empty game. I've already tested that. And now I have player A rolling a 6 and more stuff that happens. Let me just put this over here. So what we can actually do is if we look at all the where are the examples? So this is the game examples that we have. We not only have a list of examples, but we actually have an examples map. So this guy, this is the empty game, and I've got other tests which are depending on it. So I've got a whole tree of tests. And what that means is if one of the tests fails early on, I'm not going to run all of the other tests that depend on it. So I have fewer tests failing. So instead of having dozens of tests broken and say, well, which one should I start looking at? Well, I know exactly because there are a tree of tests. The one that failed is at this corner point. Yeah.
How do I ensure that
What do you mean?
like in the first
Yeah.
how do I assure that
Oh, because each example method returns an independent object. So I'll get a new instance of the game which is equal to the other one. So if I run multiple tests, each of them are going to get their own, they'll start with a new instance that's built up from that point. So there is some duplication in terms of execution, but not in terms of the code. So you get fresh instances. Yeah, that should be nice and safe. Yeah, so what I did is I broke them up into before and after examples. So here's an example where there's a corner case. What happens if a player, oh, I'm in the wrong place here. A player rolls a 6 twice. The second token lands on the square where there's already the first token. So here we can split that up into two parts. There's the setup. Player A has rolled and he got a 6. And now he rolls another 6. And player A is going to land on the square where player A already has a token, so he should land on the next place. So this is something that you can build up and have all the individual scenarios broken down with their appropriate assertions so that you can be sure that everything that's supposed to happen is. So actually tried to cover most of the situations, but maybe there's some that are still missing. Right, and then we can run all of these from the examples tab, as we saw. So those are the test examples. They're really a cornerstone. That's something that's pretty much original in GT. The origin of the examples as tests dates back some years, and I think one of the first implementations we had was for Java. If you Google for JExample, you find on our website the implementation of example methods for Java, and the last time I used it, which was only last year, it was working perfectly fine. So it extends JUnit with tests that will take arguments, which are example objects, and tests, instead of returning nothing, being void, they will return an object. And you'll find documentation about that. So if you're curious to look at that, there's the implementation, and there was also a very nice paper some dozen years ago in the XP conference on that. It's quite powerful, but somehow we didn't manage to convince people to use it in Java. So let me move ahead. Okay, so now we have these views and we have the games. The games get kind of complicated, but what's actually happening in the game and how have the tokens moved? So we'd actually like to extend the Ludo game to keep track of the history of what's happened. So we're going to create a subclass of the Ludo game called a recording Ludo game, and it keeps track of a history of the moves. And this means that we need to take a move and turn it into a first-class object. Before it was just a method. I send the message move and something happens on the board. Now I want a move object because I want to have a whole bunch of move objects that record the history of what happened over the game. So let's have a look here. Here's a Ludo recording game, and we have board as before, we have players, squares, and we have the moves. So these are the moves that have taken place so far. And we can navigate through them, and now we have a view of a move. So this tells us what's the first thing that happened was that A rolled and moved to the first square. Then A came out, the little a came out, landed on it and moved ahead. A rolled, I don't know what, we can find that somewhere as well. Again a 6, so it moved. Another 6, and it's moving all the way through the board. And finally it rolls a 5. And at this point, well, 1, 2, 3, 4, 5 would take it off the board, so that's an invalid move, and it goes back to where it was. And now A's turn is over. Of course, this is an object. Well, this is a move object, and it's not the game, but I can ask the game to replay itself up until this point, and now I got an instance of the game. So this is a game at this point, and it's a perfectly valid instance that I can then ask player B could then move, and then player C, and so on. So I could continue executing from this point in history. And I could try and do this, but I've been burned so badly already so many times. Let me just run it 10 times. Okay, 10 times seems to be okay. If I do 100, okay, it worked. So I can get to the end. And now what's cool is, let's inspect self. And look at the history. There's the actual history showing all of the moves. But I could pick any particular point in the history and go back to that point in time and continue executing the game from there. So let's see if we go here and get this move, replay game to here. And now we autoplay 100 times. And again, this time player A won again. Player A is lucky. But it could have been another one. So now we're tracking the moves, and we have actually a whole history of the game, and we can animate what is happening step by step. And this is what we just saw. We can autoplay the game with the history and go back in time. Now, what you have is not just a nice interactive environment for interactively developing the game and also exploring different states of the game, you can also now build live documentation using these bits and pieces. So here's, for example, we have one example showing 6 moves all in a row that illustrate many of the scenarios of the game. So this is, again, another example method. And we can develop a view which will give us a history of all of the steps of the game up until that point. So this is a form of documentation that we could use if we want to document how the game is working. So you have all of these different snapshots, so you can document the logic, the business view of the game. As we said with the test examples, we also have all the different kinds of scenarios, and we can take these examples, which are tests, turn them into live objects which we can plug into the documentation so that we can explain, these are the different scenarios. Here's an initial move. Here's a regular move with all of the associated visualizations. Here's an impossible move that cannot take place because you would go off the end of the board. Here's a case where you jump over one's own token, and here's a case where you capture somebody else's token. And then, because you have all of these views, you can also break them down into the individual steps that take place. So very often a move in the game is you just roll a die and a token moves. But there's certain situations where you roll, it moves, something happens, another thing happens, and yet another thing happens. And in the most complicated case, you might land on one of your own tokens, move forward, again land on another token, and that token gets sent back. So there are actually 3 steps. The simplest one, where there are no steps, you roll the die, nothing happens. So that can be quite complicated. Okay, and you have the business view, but you also have the technical solution. So once again, these things can be live. You can, for example, I don't consider this to be a final version of what UML diagrams should look like. This is here is one issue that you see. This is an automatically generated UML diagram from all of the classes in the system. And it's a little bit hard to see here because there's just too much information here. But with the zoom button, we can zoom into it and see, for example, here are all the graphical elements that have been created, the game element, die element, and so on. The elements are for the graphical elements in the game. We have all of the model elements all the way over on the left here. We have the example objects, players and tokens, the die, the square. We have the test examples. And at the very end, we have all the different kinds of announcements that are used to implement the model view controller views. Again, a problem with generated UML diagrams, they tend to be very cluttered and don't communicate much. So I personally don't recommend using automatically generated UML diagrams. Any diagram communicates what you want it to communicate. So it's much better if you can tailor the diagram to just select what you want. So here, for example, I've just selected only the model classes and I'm viewing those, which gives us already less information to look at and is easier to browse through. So we can see, okay, well, the model is just the game, the move, the player, the recording version of the game. Note that this is still all live stuff here. So if I click on this, I can navigate directly to the live class. And this is not a diagram. These are actually objects. Everything's an object. Oops, and I just moved. I moved a method out of the way because they're just elements that can be moved around. Here, this is another diagram that shows not only the inheritance hierarchy, but also the relationships between the classes. So here, for example, this is semi-generated. So I generated a view of the model classes and the relationships, and it looked terrible. So I tweaked with the layout and then saved the layout. So this is sort of the manually tweaked layout. There are, frankly, strong limitations to what you can achieve with automatically generated diagrams, and you have to put a lot of smarts into it to get something that looks halfway decent. But here already we can see much more clearly. We have the game, the original game we implemented. Here's the recording version of the game, which is a subclass that keeps track of the history. The original game has a die, which is for rolling, for picking the next number of moves. We have players and tokens, which are named entities. So I'm just using class inheritance to share some simple behavior between these classes. I have a blank token, which is a funny thing. If you look at the class comment, it says it's a kind of a null object. So null objects are there because you don't want to have null checks in your code everywhere. That's one of the worst smells. We did a lot of work over the years analyzing different kinds of software systems and doing lots of static analysis. And at one point, I had a PhD student who was very interested in what kind of bugs are common in Java code and what are common bug fixes. The number one most common bug fix is adding a null check. That's appalling. I mean, don't programmers have better things to do than check whether a variable's value is null? Anyway, the null object pattern, which you probably saw in the lecture, is something that helps you get rid of some null checks. Instead of checking, is this null, and do this, do that, you just create a dummy object which doesn't do anything. It just sits there, and instead of being null, it just sits there, and you don't have to ask if it's null. You just send it a message, and it knows that it shouldn't do anything because it's just a null object. And it may even be useful because the blank token has a blank name. So when I want to display its name, it's just a blank instead of null exception error. So that's an example of a null object there. And we can see that the recording game knows these new things that we created, which are the moves and the token moves to keep track of the history. Yeah, I think I came more or less to the end of the demo part. What are the take-home messages from my perspective? One is that Smalltalk is really an environment for live programming. Two big take-home message. Number two is example methods. They give you composable tests, and you can interact in a live way with the test results. And you can also reuse those in documentation. And then finally, the moldable development brings together the coding and the exploration of live systems. What's next? You can download all this stuff from gtoolkit.com. All of the live examples are in there. There's a book, and I'll show you very quickly. So when you download the system, you see this. This is the Glamorous Toolkit book, and it just consists of a whole bunch of pages describing GT itself, including some introductory pages, for example, an introduction to Smalltalk and so on. Right near the bottom are actually the pages that you've seen today. They're part of this guy. And if you go to the Smalltalk intro slideshow in the class comment, you can actually run that yourself if you like, if you want to browse through it and recover. And you'll find all of the implementation in the standard download. To find stuff, you can use this guy, the search button here. And if you search for G2 Ludo, you'll find all of these classes in the coder here. So here's the package and all of the classes in the implementation. Here are all the examples, of course. And as I showed you before, you can verify that everything is running as it should. If you want to know more about Smalltalk and Faro, the Faro environment looks a little bit different, so be warned. The default environment looks more like the more old-fashioned Smalltalk environments. It looks like this with a different kind of a class browser. So it has a completely different environment. So GT looks different and behaves different, but you can also default back into the more old-style Smalltalk environment. And you'll find on books.faro.org all sorts of technical documentation as well as introductory stuff. So you'll find stuff live within the system itself, but also, for example, Pharaoh by Example is the first book to start with to learn a little bit about the environment. But that describes the Pharaoh environment rather than GT. And as I said, if you want to get the starter here in the Glamorous Toolkit book, just getting started with the first few tutorials will also get you warmed up there. Okay, that's everything I wanted to show you. Sorry that we had the image freezing. Things happen. Notice this is still not a first official release. We're close to it, but we're not quite there yet. And there are a lot of platforms that are supported. So there's Windows and Linux and various Apple platforms as well. And making sure that they're always running all the time is not so easy. Any questions? Have no fear. I realize this was all very fast and the environment looks very strange and different. So any question is fair game. Shoot.
Yeah. So one thing I was wondering,
Okay.
a matter of practice because this is
I'll tell you what I do. So this is best practice. You saw the book. You get a book for free. So you get a a default Leopard database when you get started. And here's mine. And so I've created quite a few pages here with to-dos and so on. Whenever I start working, I create, so here I was preparing the P2 Smalltalk lecture. I started keeping track of things that I had to do. So I wrote myself, I start logging the things that I'm doing, and I write down little snippets. So here, for example, where's the one? Yes, I was looking for an example method. So I wanted a method that had all sorts of different syntactic features. So I said, well, how should I do that? I can write a query. So I ask object with all of its subclasses, I find all the method dictionaries, and I want the methods that have a pragma in them, and that have a comment, and they have a cascade, and they have a return, and so on and so on. And I want everything sorted by lines of code. And I run that guy, and the image will freeze on me, and it came back to me with a whole bunch of different candidates here, 72 different methods in the system that have different kinds of pieces of information here. So this one is the shortest one that has all of the things that I was asking for. But it's a method that I can't explain what it is to you. It's just, I don't know what this is. So maybe there's some more interesting ones. So when I'm doing all of these things, I keep a log. So whenever I start working, I just add a page to my Leopard database. So what it's going to do, everything's in the image, but it also creates these files which are in a folder in your system. And where is it? So this in particular is here, contents. And it's just JSON. So it's a JSON file. So what I recommend you to do, when you start playing with the system, create a note. So you just say, I want a new note. And you give it a name, playing with GT. Then you say, oh, well, I want to do something. How do I blah, blah, blah. And then I add a snippet. Oop, come on. Oh, no, it's here. Usually I do this by keyboard shortcuts. So here I have a Pharaoh snippet, and then I can add a code snippet. So I have text snippets and code snippets, and then I can type stuff and try it out. So all of my experiments, I just keep them in a file, which is a note page, and it's there, and I can always go back and enter it. So then I can just keep track and say, okay, add a new text snippet, and I keep track of the things that I've done and how I got there. Because otherwise you get completely lost. You did stuff and then you don't remember how you got there. So I would recommend you start doing all your experiments, all the questions you ask, you add them. and then try and create as many pages as you can for different topics. So here I had for the Ludo exercise, these are the pages I didn't show you. So here I had an outline of the things I wanted to do. Here I took the actual exercise description, since it's all markdown, and I just loaded Pooja's description into GT itself, so it's there. And then I said, okay, well, I want to create the basic Ludo board model. So I started writing here and logging what did I do, so that when I come back to it a few days later, I remember. And then adding simple list views and keeping track of everything. So keep a page for every little thing. So that's what I would recommend you to do. And it helps you to organize your thoughts. It was a long answer to a short question. I don't know if that answered the question. Yeah, one thing that you can do is usually you've got a series of messages. So I start exploring an object, I send some messages to it, I get a new object to explore, and so on. So, well, how did I get there? Then I go back to the beginning and say, well, if I type in this expression, that gets me to that window much faster. So now I have a new snippet, and then I can test that and say, okay, now I know how to get to that stage. So very often that's the case. I say, oh, gee, I wish I had that situation today where I had, the slideshow itself, and I wanted to see how do I have a view of the slideshow page. So where was that? No, this one I should have. Yeah, so if I inspect this guy, at first I didn't see anything here. I was missing the live view. So I said, well, how do I get this live view? And there was some different code. I had to start navigating around. So how do I generate the live view of this particular slide and this location when I click on it so that I see it? So then I had to start navigating around. Once I found the code, I actually realized there was something more complicated, and I needed to add this method here, which didn't exist. So there was an as element method that had to be added to make this much, much simpler than it was before. Yeah, so you start navigating and navigating. So how do I get there? And then you pull back and then create a new method or add a new snippet. It helps you not get lost. Other questions? What can I tell you to not make you intimidated about trying to play with the environment? So, I mean, Think was created more with the idea of helping customers. So their real use case is they want to make systems explainable. So you don't only want to be talking to technical people, but talking to business people. So what they've done is with the help of these tools, so very often you have a company that has a ton of existing legacy code, and they've completely lost track of what's going on there. So there's a very large telecom company that they're working with now that has a huge amount of software with lots of different kinds of feature tags, and they've lost the overview of it. So what the team at Think did is they take all of this software, suck it into a Smalltalk image so you can build a model of it so that you can then start building different kinds of visualizations and asking questions about it. So it's software on the one hand, but on the other hand, it's data. And then by getting dedicated views, as people start a dialogue about them, you build new views very cheaply. As you saw, some of these views are very small. There are a lot of tools built in to make it easy to create new visualizations and get to the point that you start having a dialogue with not just the technical people, but with the business people. And you can sit together with business people and show them these things and just show them all the visualizations, and you can start wandering through the whole massive amount of data and start answering questions about what would be the impact of this or that. Notice, if you take 1 million lines of code, you can't read it and you can't show it to the CEO. But if you have 1 million lines of code or 10 million lines of code, you can build a model of it. And if you know how to build models, you can build dedicated views and visualizations that can start answering the questions. Notice you can't do that with a closed tool. You can't take an off-the-shelf tool, load in the software, and magic will happen and it'll answer all your questions. It has to be an interactive process. You have to be able to design and build the model the way it needs to be to answer the questions that people have. You have to understand what it is that they want to achieve, and you have to build these dedicated little views. But if the environment is there and all the tools are there, that can be cheap and can be done in the matter of hours or days or at most weeks instead of months and months. So that's really the killer use case for me. So you have lots of data, you don't know where you are, and you want to build some kind of models that you can then answer interesting questions about to make business decisions. One of the big failures, I think, of modern IDEs is that they're not much more than glorified editors. You're looking most of the time at text. And what I tried to show you today is we didn't look too much at text. You saw some snippets and so on, and occasionally we dove into the IDE, but most of the time we were navigating through different kinds of examples to try and get a feeling of how all of these live objects are connected to each other. So that's the way we think it should be. You should be much more interacting with the code than just staring at source code. Yeah? No, it doesn't need to be translated to Smalltalk. I mean, code is just data. So we have some compiler experts in the Fink team, and they have some pretty amazing compiler technology. So you can write parsers that help you build ad hoc parsers for whatever information that you want. Note that when you build a compiler, you need a certain very fine-grained information about the source code. But when you're answering these kinds of questions about understanding the code, you don't necessarily need a full parser. So you may have a coarse-grained parser that extracts certain information about the code and ignores other parts, things called island parsers. Yeah?
But, I mean, as a follow-up question, then if it's just data, hours, and we can do data analysis,
Well, you can. So we have language bridges, I think for the moment, I haven't used them myself, but to Python and JavaScript. So when you're analyzing those codes, you can actually have a bridge to another platform which will execute stuff for you. So you can have the model and all of the live stuff in Smalltalk, but you can also execute the code on some other machine.
some magic then.
Yeah. You don't need to translate the code to Smalltalk, but you may need a bridge to another environment if that's what you need.
Yeah.
Good. Anyway, if people have questions about this offline, I'm also available. You can find me easily, I'm sure. I will be leaving on vacation in a couple of days, but I'm accessible by email, so I can answer questions. And I'm always interested if people want to dive a little bit more deeply, so have no fear. There's also a community on Discord for Glamorous Toolkit. So you can find that from the G Toolkit page. There's a link to the, where is it? To the Discord. Where is it? Contact or about? Somewhere. Discord chat, yeah. So there's a Discord where you also have a nice community for answering questions. Okay, then I guess I'm done. Thanks very much.
So maybe before all of you disappear into a short break, so let me maybe. The students on the stream can follow us. So first of all, thanks again, Oscar, for giving us this very inspiring lecture. And I have to add that you only saw these 90 minutes that Oscar was here, but I can say that he was preparing this actually for weeks and programming on the Ludo. I mean, you had a lot of fun probably. But it was also a lot of work, so once again, thanks for this. Then maybe regarding the what's next, so at least as long as Oscar and Pooja are there, and maybe they even manage to transfer some of the knowledge to me, you can also dive deeper into this, for example, in a seminar, which you will have to take later on during your study course anyway. And so this is maybe a good option to dive deeper into this and to play with it. And then, of course, there are also bachelor topics and later on master topics. So, yeah, if you're interested in these topics, then just contact me or Pooja or directly Oscar, so he's still available here. That's it for this. And then I have to say that I heard in the break that in KSL the registration for the exam so far does not work. So maybe it's me that who has to activate this. I will have a look at it. So, but don't wonder if it's not working now. I will have a look at it, and it should work next week. And yes, also think of the fact that the course evaluation is still open. So please, we need your feedback. I once posted the links on the Elias chat, and take these few minutes and give us some feedback for the course. Okay. Yeah, thanks. That's from my side, and now you have to negotiate with Pooja about the length of the.
No, there is no exercise. Our Oscar covered pretty much everything today. So
Okay, everything is okay.
But the exercise is already available, and I tried to give description what it is about, what are the components. Yeah. So the exercise is now published just few minutes ago, and you can have a look. So it's basically about the same examples which Oscar told us about, what GT Ludo game, where basically you have different components, model, view, controller, UI, and you explore through those examples, and your task is basically to create one example or one test case to test if a player has occupied a square of another player. So basically, you have to check only one, or you have to create only one test case, one example. And there are various examples available in that class. So make sure you browse through them, you understand how it works. And it's a very simple exercise. It's an optional exercise, as we promised in the starting of semester that there will be 2 optional exercises. But I will strongly encourage you to try this environment. Good for, it will prepare you better for the exam also. And yeah, so please look at the exercise description. If you do not understand, feel free to write on Discord and write to Oscar about if you want to know about the environment, or also to me. Good. The deadline is 1 week as usual. First, 27th. Next Next week. No, 27th. Maybe then it's a, yeah. It's the same 1 week deadline that we usually have. Any other question? And next week we will also, no, I think it will be next to next week we will have exam preparation session on 3rd of June. Yeah, that's good. Good, thank you. And thanks again to Oscar.